Hello and good day. Your Excellencies, Dr. Mahmoud AbuZeid, the President of the Arab Water Council, Dr. Hussein El-Atfy, the Secretary General of the Arab Water Council, distinguished guests, dignitaries, friends, colleagues, professionals, practitioners, and the ICID family. First of all, I would like to thank the Arab Water Council for inviting me to deliver this presentation. The presentation is about water saving and irrigation using new technologies for accurate estimation of crop water requirement and efficient irrigation systems. Crop water requirements commonly estimated by either equations or measurements. The measurements could include soil moisture, sap flow, lysimeters, and direct measurements by bound ratio, ED covariance, or centilometers. When we started to measure the evaporation, we started by the Class A pan evaporation, and then with the weather station's availability, some equations were developed to use the wind speed, net radiation, temperature to calculate the evapotranspiration. However, the first equation that included, in addition to meteorological data, the plant parameters was the equation of Penman-Monteith, 1965, where actually introduced, in addition to meteorological data, the RS parameter, which represents the crop resistance to evaporation. However, that resistance to of the canopy was troublesome to some practitioners, and have been looking for a simplified form of this equation, and ICID and FAO cooperated in trying to find a simplified formula by using an average seasonal value of canopy resistance of several crops. And that value was found to be 70 seconds per meter. And when it is introduced into the original Penman-Monteith equation, and that equation became in that form, where you don't see at all the crop parameter, which was represented in the original Penman-Monteith was RS, or the canopy resistance. However, actually, the resistance of the stomata resistance, it varies during the day, and from midday to midnight, it varies. It has a sine wave shape, and also during the season, it differs from 1 month to another, and during the season. So this really quite an approximation that has been used in the modified equation by ICID and FAO. And the modified equation was published in the FAO Irrigation Range Report number 56, and has been widely used all over the world. And we tried to compare the evapotranspiration calculated by the modified FAO ICID equation of Penman-Monteith, and to test it against direct measurements of ED covariance and centrometry. And we had a site in north of Italy, which was part of the European funded project Water for Crops. And the centrometry and ED covariance were placed in there, in addition to the Cosmos, and I'll talk about Cosmos in a minute. But the ED covariance, actually, it is a direct measurements of the actual evaporation. And here you have those sensors, and it calculates actually the horizontal flux of air, and that direct flux of the air between those sensors represents the actual evapotranspiration over the crops. The other instrument we used was the centilometers. Centilometers has two parts, a transmitter and receiver. And the transmitter would transmit optical infrared with micro radio waves from that point, and the receiver would be at the far end, and that far end could be up to 10 kilometers away. And it looks at the change in the air and the air density between the transmitter and the receiver. And the change in the density of the air actually is a function of the evapotranspiration and the change in density is caused by the change in temperature and the relative humidity. And from these, actually, we can calculate the actual evapotranspiration over a transect of up to 10 kilometers over different crops between the transmitter and the receiver. And we can do analysis of the footprint between the transmitter and the receiver. And that footprint analysis would allow us to identify how much the evapotranspiration came from each crop on the transect. So, for example, here that wheat and maize and tomato, their contribution to the total evaporation can be identified by analyzing the data of the centrometry. And when we compare what we obtained from the eddy covariance and centrometers with what we obtained from the calculations using the modified Penman-Matisse of FO56, and you can see here that the orange and blue dots here are the centrometers and eddy covariance, actual evapotranspiration direct measurements. When you compare it with the continuous gray line of ET node or reference evapotranspiration calculated by equation, you find actually the eddy covariance centrometers well below what we calculate from the equation as a reference evapotranspiration. And if we calculate also the crop evapotranspiration using the modified equation, which actually the yellow dot here, you can see those yellow dots well above what we measure as actual evapotranspiration by the eddy covariance and centrometers. And in some cases, actually, the actual evapotranspiration measured by centrometer eddy covariance could be between 44 or 34% of what we calculate from the modified equation. This is quite a difference in calculating the crop water requirements. And there was some supporting findings found also by the others, and some also scientists in India using lysimeters and a potato, they discovered that the Penman-Matisse modified equation gave a lot higher estimation of crop water requirements. And also in Jordan Valley, using the eddy covariance on tomato, they found also that the measurements of eddy covariance gave 36% lower values than the equation of FEO, and also in Portugal over orchards, and also using the eddy covariance, they found there is an overestimation of the equation compared to what they measure in the field. So calculating the reference AT node or crop water requirements from meteorological data produced a potential evapotranspiration, and that's a lot higher than what we measure actually from direct measurements, because the meteorological data would actually represent the atmospheric demand for water rather than the crop demand for water. And accurate water requirements should be based on crop demand rather than atmospheric demand for water. And that brings us to another issue of the deficit irrigation. A lot of scientists use deficit irrigation as a ratio of the total crop water requirements. And most of the scientists, they found that when they irrigate with 50% or 60% or 70% of the total requirements, they get the same yield as when they apply 100% of the full requirements when it is calculated from those equations. And the issue now, and the question is the deficit irrigation really a deficit, or it is just an actual requirement, and the full irrigation requirement was exaggerated due to the overestimation by the method used, like this FAO modified equation, to determine the crop water requirement. And there are some publications here. And another way to calculate the crop water requirements is to look at the soil moisture deficit of the root zone. And soil moisture, we have been using over the years soil cores, neutron probes, profile probes, electric resistivity tomography transects, and also we used a different indirect methods with sensors. But recently, and based on the findings of Victor Hess from Germany, and using his hot air balloon, he found that there's outspace radiation that as a cosmic rays is really quite exceptionally high penetrating capacity, and also ionized air at the Earth's surface. So what he found is that when you have the cosmic rays coming from outer space and comes closer to the biosphere, closer to the solar surface, it interacts with the biosphere and generates neutrons. And those neutrons, they have the same atomic weight of hydrogen. And when they collide with the hydrogen, which is mostly exists in the soil moisture, then they slow down and they are not fast anymore. So if we can have tubes or sensors, they can detect how many of those neutrons slowed down, then we can have an idea about how much water and how much hydrogen exists in the soil moisture. So the idea of the cosmic rays was translated into a device, and now this device is those sort of sensors, and the measurement now can cover a large scale, which is area based, between 300 and 700 radius, and non-invasive, of course, because it's natural radiation, and it gives a more representative soil moisture based on area, not a point scale, and could help us to get the soil moisture deficit. All over the UK, we have about over 55 stations where we monitor the soil moisture using those Cosmos, and also we have a network in India and also in China, and there are some other African countries now they started to use that, and we have a website, and the measurements goes directly through online facilities to the server, and you can go and check on whatever site on the soil moisture of that site on a certain day. And soil moisture, of course, not only used for irrigation, but also used for drought monitoring and the flood forecasting and the groundwater recharge, and so many applications. And in our experimental field, we applied the Cosmos, and here you have the soil moisture Cosmos in response to the rainfall of that period, and we could color code actually the soil moisture deficit. When it is green, it means no need to irrigate. When it's yellow, very mild stress, and when it's orange or red, then it is indication that we might need to irrigate. And when we compare the soil moisture of the Cosmos with other methods like the cores, like profile probes, like sensors, and we found that they are very close to each other with a minimum value really here for root mean square error. So we can use that soil moisture deficit to calculate the total amount of water need to be applied for irrigation, and we can save a lot of water as well. And the Cosmos also can detect the soil moisture on the top 60 to 80 centimeter of the soil, which most of the roots actually do exist in that part of the soil layer. And there are some also publications related to the Cosmos applications, and there was a press release by Wiley to announce about this new methodology. And saving water can also be by improving water use efficiency. And improving water use efficiency can be by adopting more modern and efficient irrigation system, also minimizing the losses of seepage and leakage and evaporation, and also by automation of the irrigation system. If irrigation efficiency can vary from the reservoir to the crop, and it could go down from 70% at the reservoir all the way to 35% to the plant because of the losses across the transport of water from the reservoir to the field. And when we think about if we can save water by changing the irrigation system, this is an example here of how can we save water, especially for rice, because rice is subjected always to flood irrigation. And you can see here that we can save water up to 70% if we irrigate rice by drip irrigation, and we can have increase in the yield by 40%, and we can have also saving in the energy by 60%. And we can also save in the fertilizers and also avoid mosquito-related diseases. And also there is no methane emission under drip irrigation compared to flood irrigation, and also can minimize the nitrate leaching to water bodies. Also, we tried that in the Mauricio Island, where we also applied drip irrigation for sugarcane instead of the furrow irrigation. Also, having a low-level nozzle for center pivot closer to the ground would save up to 30% of water because of the evaporation and wind effect with the high nozzles of center pivot. Also, with drip irrigation, putting the drip lines under the surface by applying the subsurface drip irrigation would also save a lot of water by avoiding the losses by evaporation from the soil surface. In addition, we can also do more saving by applying partial root drying method, where we have twin tubes here, subsurface, and about 10 to 12 centimeters below the surface. And we have the plant in the middle. We only apply irrigation to one side, like the blue one, for that irrigation, and the following irrigation we apply to the other side of the plant. So at any time, we only irrigate half of the root zone and we alternate from one side to the other. And that actually allowed us to save about 26% water compared to the classic or conventional drip irrigation. But when it is compared to sprinkler irrigation, we can save up to 44% when compared to sprinkler irrigation. And more than that, we are now moving towards nano irrigation, which is a low flow and for a longer period. And most of the time, we use a semi-permeable lines or tapes to irrigate for a longer period. And this is an example of those drip irrigation tapes perforated with small holes that would allow water to seep for a longer period and at a low rate. And it actually gives us a high efficiency, almost up to 95%. And we lose only less than 5% water. So you can save a lot of water when it comes to using that nano irrigation system compared to the flood irrigation here, where we lose a lot of water. It could be sometimes really quite high. And another also system appeared now to be in use, and it's the ultra low drip irrigation system. And ultra low drip irrigation system actually gives the flow 0.1 to 0.3 liters per hour instead of the conventional drip system 2 to 4 liters per hour. And it's a long period, of course, to irrigate, and it keeps the soil moisture closer to the root zone and not below. While the conventional drip irrigation, you can find some water still goes below the root zone, and that's of course a lost water. So in order to save water, it could be better to use the nano irrigation or the ultra low drip irrigation, where we confine the water only to the root zone, and we can save up to 30% of the irrigation water. And another system also now coming to the market by center pivot companies is the varying irrigator rate VRI technology, and that depends on the GPS and GIS, and where actually the center pivot here arm has got a variable rate to irrigate the areas below. For example, if we have a light soil and ditch and heavy soil under the arm here, so you can expect it to have more water coming to the light soil section. No water need to be applied to the ditch, and you can have here a lighter amount of water applied to the heavy soil when it is compared to the light soil. So you can have that sort of mosaic. So not everywhere gets the same amount of water, but you have different amount of water according to the heterogeneity of the place under the center pivot. And also we can minimize the losses by evaporation on the open channels by covering it by solar panel. And also we can cover the reservoirs by floating a panel, solar panel, and that would also minimize the evaporation, and we can save water and produce more electricity. Thank you very much. I hope you enjoyed the presentation. Thank you.